This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Welcome to an exploration of the fascinating evolution of hearing. Prepare to embark on a journey from the earliest whispers of life in ancient oceans to the complex soundscapes we experience today. We'll unravel the mysteries of how ears evolved, from simple vibration detectors in fish to the sophisticated auditory systems of mammals. Discover the remarkable adaptations that allow animals to perceive and interpret the world of sound, from the echolocation of bats to the infrasonic rumbles of elephants. Join us as we uncover the secrets of the ear and the symphony of sounds that shape our lives. Chapter 1. A World of Whispers, the Dawn of Hearing. Imagine our planet, eons ago. Continents huddled in unfamiliar arrangements, and beneath the waves, life pulsed in a symphony of vibrations. Long before the delicate architecture of the mammalian ear, before the coiled wonder of the cochlea, there was a different kind of listening. A world perceived through subtle shifts in pressure and the dance of water against skin. This was the realm of the lateral line, a sensory masterpiece etched into the bodies of the earliest vertebrates, the fish. These weren't ears as we know them, but rather an intricate network of finely tuned receptors, like a living, breathing seismograph, mapping the underwater world. Picture a delicate tracery of pores and canals, running along the flanks of a fish, branching onto its head, a sensory web connecting it intimately to its surroundings. Within these canals, nestled like tiny sentinels, lie the hair cells, the fundamental building blocks of this remarkable system. Each hair cell is crowned with a cluster of cilia, microscopic hair-like projections that extend into a gelatinous dome called the cupula. As water moves around the fish, it enters the pores of the lateral line, flowing through the canals and nudging the cupula. This subtle deflection, in turn, bends the cilia, triggering a cascade of electrochemical signals that race along nerve fibers to the fish's brain. This is the language of the lateral line, a language of vibrations translated into nerve impulses, painting a vibrant sensory landscape for the fish. It's a language of currents and eddies, of the pressure waves generated by a struggling prey or the looming presence of a predator. It's a language that allows fish to navigate murky waters, avoid obstacles, and even coordinate their movements within a school, all without relying on sight. Consider the blind cavefish, dwelling in the perpetual darkness of subterranean caves. Sight is useless in their world, yet they navigate with astonishing precision, their lateral lines acting as their eyes. The slightest disturbance in the water, the echo of their own movements bouncing off cave walls, is captured by their hypersensitive lateral lines, creating a three-dimensional map of their surroundings. Or picture a shark, a formidable predator, homing in on its prey. Its lateral line, a finely tuned instrument of detection, picks up the low-frequency vibrations generated by the injured fish, guiding the shark through the darkness or the chaos of a feeding frenzy. Even the seemingly placid goldfish, a common inhabitant of our aquariums, relies heavily on its lateral line. It helps them maintain their position in the school, sense the approach of a net, and even detect the subtle vibrations of food hitting the water's surface. But the lateral line is more than just a sophisticated tactile system. In some fish, it also represents the earliest precursor to what we recognize as hearing. While all fish can detect water movement through their lateral lines, some species have evolved specialized structures that allow them to perceive sound vibrations, opening up a whole new dimension of sensory experience. This transition from feeling vibrations to hearing them involved a series of evolutionary modifications. In certain fish lineages, parts of the lateral line system became associated with air-filled cavities, such as the swim bladder. This structure, primarily used for buoyancy control, could also act as a resonator, amplifying sound vibrations and transmitting them to the inner ear. In some species, like the goldfish, a chain of small bones, called Weberian ossicles, evolved to connect the swim bladder to the inner ear, further enhancing the transmission of sound. This was the genesis of hearing in fish, a rudimentary form of auditory perception, limited to lower frequencies and lacking the sophistication of the mammalian ear. It was a world of muffled rumbles and thumps, a far cry from the rich tapestry of sounds we perceive. Yet, it represented a giant leap forward, a crucial step in the evolutionary journey toward the complex auditory systems of land vertebrates. The transition from a purely tactile sense of the underwater world to a world of sound presented numerous challenges. The detection of water movement is a direct, physical process, the copula being pushed and pulled by the flowing water. Sound, on the other hand, is a more elusive phenomenon, a pressure wave traveling through the water, requiring specialized structures to capture and amplify it. Imagine the sensory confusion of those early vertebrates, their lateral lines bombarded by a mix of tactile and auditory signals. Distinguishing between the caress of a current and the distant rumble of a predator, between the vibrations of a struggling prey and the subtle shifts in water pressure, would have been a crucial survival skill. Over millions of years, the nervous systems of these creatures evolved to decipher this complex sensory input, gradually separating the tactile from the auditory, the feeling from the hearing. This was a gradual process, a slow awakening to the world of sound, a world of whispers that would eventually evolve into the symphony of sounds we experience today. This rudimentary form of hearing, however, had its limitations. The frequency range was narrow, and the ability to localize sounds was rudimentary. The world of sound, for these early vertebrates, was still a blurry, indistinct landscape, lacking the clarity and precision of later auditory systems. Yet, it was a world that had begun to speak, a world that would continue to unfold its sonic secrets in the chapters to come. Chapter 2. From Jaw to Ear, a Symphony of Bones. The transition from water to land presented vertebrates with a formidable acoustic challenge. Water, a dense and supportive medium, transmits sound waves efficiently. Air, in contrast, is far less dense, creating an impedance mismatch that hinders the transfer of sound energy to the fluid-filled inner ear. This mismatch posed a significant obstacle for the first terrestrial vertebrates, demanding innovative solutions for detecting airborne sounds. Early reptiles, emerging from their amphibian ancestors, inherited a simple hearing system. Reptiles relied on a single ossicle middle ear. This system consisted of a single bone, the columella, stapes in mammals, which connected the eardrum to the inner ear. Sound waves striking the eardrum caused the columella to vibrate, transmitting these vibrations to the fluid-filled inner ear, where they stimulated sensory hair cells. This single ossicle ear, while functional, had limitations. It was primarily sensitive to low-frequency sounds and lacked the sensitivity and frequency range of the mammalian ear. The upper frequency limit in most reptiles is estimated to be around 5 to 8 kHz, far lower than the range of many mammals. This restricted auditory world likely reflected the acoustic environment of early reptiles, where low-frequency sounds, such as ground vibrations and the calls of larger animals, were the dominant auditory cues. The transition to the mammalian three-boned middle ear was a pivotal event in the evolution of hearing. This transformation involved a remarkable repurposing of existing structures. Bones that originally formed part of the reptilian jaw, the quadrate and articular, gradually migrated and became incorporated into the middle ear. This evolutionary journey is documented in the fossil record, providing a glimpse into the step-by-step process of this remarkable transformation. One of the most compelling examples of this transition is Morganucodon, a small, shrew-like creature that lived during the late Triassic and early Jurassic periods. Morganucodon and other transitional forms possessed a dual jaw joint, a crucial intermediate stage in the evolution of the mammalian middle ear. They retained the ancestral reptilian jaw joint, where the articular bone of the lower jaw articulated with the quadrate bone of the upper jaw. Simultaneously, a new, mammalian jaw joint was forming, where the dentary bone of the lower jaw, which carries the teeth, articulated with the squamosal bone of the upper jaw. As the dentary bone enlarged and took over the primary role in jaw articulation, the quadrate and articular bones, no longer essential for chewing, were freed to take on a new function. They gradually reduced in size and migrated towards the middle ear, where they joined the columella to form the three-ossicle chain. The malleus, derived from the articular, the incus, derived from the quadrate, and the stapes, derived from the columella. This new three-boned middle ear offered significant mechanical advantages. The malleus, incus, and stapes act as a lever system, amplifying the faint vibrations of the eardrum and efficiently transferring them to the oval window of the inner ear. This lever action effectively overcomes the impedance mismatch between air and the fluid-filled inner ear, allowing mammals to hear a wider range of frequencies with greater sensitivity. The upper frequency limit in early mammals likely extended well beyond the reptilian range, possibly reaching into the ultrasonic range for some species. The evolution of the mammalian middle ear was likely driven by a number of selective pressures. The ability to detect higher-pitched sounds would have been advantageous for locating insect prey, particularly at night. Improved hearing would have also enhanced communication, allowing for more complex vocalizations and social interactions. The nocturnal lifestyle of many early mammals, often cited as a key driver in the evolution of mammalian hearing, would have placed a premium on auditory acuity in a world where vision was limited. The three-boned middle ear is a defining characteristic of mammals, but its structure and function vary among different groups. Monotremes, the egg-laying mammals, have a relatively stiff middle ear, limiting their hearing to lower and middle frequencies. Marsupials and placental mammals, in contrast, have more flexible middle ears, enabling them to hear a broader range of frequencies, often extending into the ultrasonic range for smaller species. For example, some bats can hear frequencies well above 100 kHz, using these ultrasonic calls for echolocation. This transformation of the middle ear laid the foundation for the further development of the mammalian cochlea, the spiral-shaped structure in the inner ear that houses the sensory hair cells. The increased sensitivity and frequency range of the middle ear would have created selective pressures for a more refined and specialized inner ear, capable of processing these enhanced auditory signals. This coevolution of the middle and inner ear led to the remarkable auditory capabilities of modern mammals, a topic we will explore in the next chapter. Chapter 3. The Cochlea, a Spiral of Sound. The story of hearing continues its journey inward, past the delicate dance of the ossicles, to the inner sanctum of the ear, the cochlea. This spiral-shaped structure, reminiscent of a snail shell, isn't just a passive receiver of vibrations. It's an active and intricate analyzer, a biological prism separating the complex mixture of sound waves into their constituent frequencies, transforming mechanical vibrations into the electrical language of the brain. Imagine the cochlea as a fluid-filled chamber, intricately subdivided into three parallel canals: the scala vestibuli, the scala media, and the scala tympani. The scala vestibuli and scala tympani, filled with perilymph, a fluid similar in composition to cerebrospinal fluid, flank the central scala media, which contains endolymph, a potassium-rich fluid crucial for the transduction process. These three canals spiral together around the medullas, the central bony core of the cochlea, like threads winding around a spool. Separating the scala media from the scala tympani is the basilar membrane, a flexible ribbon of tissue that stretches the length of the cochlea, narrowing and stiffening from apex to base. This gradient of stiffness and width is the key to the cochlea's remarkable frequency selectivity. When the stapes, the last ossicle in the middle ear chain, vibrates against the oval window at the base of the cochlea, it sets the perilymph in the scala vestibuli into motion. This pressure wave propagates through the fluid, causing the basilar membrane to vibrate. Crucially, the basilar membrane doesn't vibrate uniformly. Due to its varying stiffness, high-frequency sounds cause maximum displacement near the stiff base, while low-frequency sounds travel further along the membrane, peaking near the more flexible apex. This tonotopic organization, a frequency map laid out along the length of the basilar membrane, allows the cochlea to decompose complex sounds into their component frequencies, much like a musical instrument separates the notes of a chord. For example, the high-pitched squeak of a bat, used for echolocation, would stimulate the base of the basilar membrane, while the low rumble of an elephant's call would create a traveling wave that peaks near the apex. In humans, the most sensitive frequency range, crucial for speech perception, falls between 1 and 6 kHz, activating a specific region along the basilar membrane. This frequency mapping is incredibly precise, enabling us to distinguish between sounds that differ by only a fraction of a hertz. Sitting atop the basilar membrane is the organ of Corti, the heart of the transduction process. Here, nestled among specialized supporting cells, lie the sensory hair cells, the true transducers of sound. These cells are arranged in rows, with a single row of inner hair cells and 3 rows of outer hair cells. Both types of hair cells are crowned with stereocilia, hair-like projections that extend into the endolymph and make contact with the tectorial membrane, a gelatinous structure overhanging the organ of Corti. The movement of the basilar membrane, driven by the incoming sound wave, causes a shearing motion between the basilar and tectorial membranes. This shearing force deflects the stereocilia on the hair cells, triggering the opening of mechanically gated ion channels. The endolymph, with its high potassium concentration, bathes the stereocilia. When the ion channels open, potassium ions rush into the hair cells, depolarizing them and generating an electrical signal. This electrical signal is then transmitted to the auditory nerve fibers, which carry the information to the brain. Inner hair cells are the primary sensory receptors, responsible for sending the majority of auditory information to the brain. Outer hair cells, in contrast, play a more complex role. They possess a unique motor protein called prestin, which allows them to change their length in response to changes in membrane potential. This electromotility of outer hair cells amplifies the vibrations of the basilar membrane, sharpening frequency tuning and increasing sensitivity, particularly at higher frequencies. This cochlear amplifier, as it's known, is a crucial feature of the mammalian ear, contributing to its exceptional auditory acuity. The mammalian cochlea, with its coiled structure, intricate arrangement of hair cells and supporting structures, and active amplification by outer hair cells, is particularly specialized for high-frequency hearing. This specialization contrasts with the simpler auditory organs of reptiles and birds, which lack outer hair cells and the associated cochlear amplifier. The longest lizard papillae, for example, are only about 2 mm long, containing around 2,000 hair cells, and their upper frequency limit is typically around 5 to 8 kHz. Avian papillae can reach up to 11 mm in length, with the highest frequencies detected around 12 kHz, as observed in the barn owl. The coiling of the mammalian cochlea, absent in the simpler, banana-shaped cochleae of monotremes, contributes to both its efficiency and its increased frequency resolution. The spiral arrangement allows for a longer basilar membrane within a compact space, increasing the area available for frequency discrimination. The curved shape of the coiled cochlea also focuses acoustic energy toward the apex, enhancing sensitivity to lower frequencies. This coiling, along with the specialized features of the organ of Corti, allows mammals to hear a much broader range of frequencies than reptiles and birds, often extending into the ultrasonic range for smaller species like bats, which use these high frequencies for echolocation. In larger mammals like elephants, the cochlea is tuned to lower frequencies, important for long-distance communication. Even within mammals, there's significant variation in cochlear size and shape, reflecting the diverse auditory needs of different species. The longer cochleae of some mammals, such as dolphins and bats, enable finer frequency discrimination, crucial for echolocation and underwater communication. Humans, while possessing relatively long cochleae, have a lower upper frequency limit compared to many other mammals, likely related to our larger head size and the acoustic properties of our vocalizations. Interestingly, humans show an unusual trend in frequency selectivity as a function of frequency, possibly influenced by the development of speech. The cochlea, then, is more than just a passive receiver. It's an active and dynamic analyzer, a symphony of specialized cells and structures working in concert to transform the whispers of the world into the vibrant tapestry of sound we perceive. It's a testament to the power of evolution, shaping the ear to meet the specific auditory demands of different species and environments, a story that continues to unfold even today. Chapter 4: The Sonic Landscape. The world is a symphony of sounds, a vibrant tapestry woven from the whispers of wind through leaves, the crash of ocean waves, the chirps of insects, and the calls of animals. Each environment, from the abyssal depths of the ocean to the windswept peaks of mountains, presents a unique sonic landscape, shaping the evolution of hearing in the creatures that inhabit it. In the ocean's embrace, marine mammals have evolved astonishing adaptations for underwater acoustics. Toothed whales, like dolphins, navigate and hunt in murky depths using echolocation. They emit high-frequency clicks, generated in their nasal passages, which then travel through specialized acoustic fats in their foreheads, acting like lenses to focus the sound waves. These clicks bounce off objects in their path, and the returning echoes, captured by the lower jaw and transmitted to the inner ear, paint a sonic picture of their surroundings. The size and structure of the middle ear bones in toothed whales are adapted for receiving these high-frequency echoes. Smaller ossicles, with less mass, can vibrate more rapidly in response to these high-pitched sounds. Baleen whales, the gentle giants of the ocean, face different acoustic challenges. They communicate across vast distances using low-frequency calls, which can travel for hundreds or even thousands of kilometers underwater. However, these low-frequency sounds are increasingly masked by the din of human activity, from ship engines to sonar and seismic surveys. The larger ossicles in the middle ear of baleen whales are better suited for detecting these lower frequencies, but the escalating noise pollution in the oceans threatens their ability to communicate and navigate effectively. On land, the auditory adaptations are equally diverse, reflecting the varied acoustic properties of different habitats. A crucial factor influencing a mammal's hearing range is its head size. The smaller the head, the smaller the distance between the ears, and the higher the frequencies it must hear to effectively localize sounds using interaural intensity differences, the differences in sound level between the two ears caused by the head's sound shadow. Smaller mammals, like mice, have evolved exceptionally sensitive high-frequency hearing, extending into the ultrasonic range. This allows them to detect the ultrasonic calls of insects, a rich food source, and to hear the rustling approach of predators like owls, whose soft feathers muffle their flight sounds at lower frequencies. Larger mammals, like elephants, communicate across the open savannas using low-frequency rumbles, infrasonic calls that can travel for kilometers through the air and even through the ground. These low frequencies are less affected by obstacles like trees and vegetation, ensuring that the calls reach distant herd members. Elephants, with their large cochleae, are tuned to these low-frequency rumbles, while the shorter cochleae of mice are specialized for detecting higher frequencies. Some mammals have even relinquished high-frequency hearing altogether, adapting to the unique acoustic demands of their environment. Subterranean rodents, like the naked mole rat, live in a world of near-constant darkness and rely primarily on tactile and olfactory cues. High-frequency sounds are quickly attenuated in their underground burrows, rendering them less useful for communication or predator detection. Consequently, these rodents have lost the ability to hear high frequencies, their auditory systems specialized for the low-frequency sounds that travel effectively through the ground. Lizards, despite being a relatively closely related group, exhibit striking variations in their hearing abilities, reflecting the diverse habitats they occupy. The structure of their hearing organ, the basilar papilla, a simpler version of the mammalian organ of Corti, varies significantly between species. Some lizards, like geckos, have specialized high-frequency hearing, essential for detecting the calls of insects in their nocturnal world. The basilar papilla in these lizards has distinct regions specialized for different frequency ranges, with the high-frequency region containing hair cells with shorter, stiffer stereocilia, tuned to higher vibrations. Other lizard families, like skinks, are more sensitive to low-frequency sounds, crucial for detecting ground vibrations and the movements of larger predators. Their basilar papillae are generally shorter and less differentiated, with hair cells tuned to lower frequencies. For example, the bobtail skink, native to Australia, has a basilar papilla that is particularly sensitive to the low-frequency vibrations produced by its insect prey moving through the leaf litter. Birds, masters of the air, have evolved a diverse array of auditory adaptations. Owls, renowned for their exceptional hearing, possess asymmetrical ear openings, one higher than the other. This vertical offset allows them to precisely pinpoint the location of prey, like scurrying mice, in the darkness below. The barn owl, in particular, has an elongated basilar papilla, providing enhanced frequency resolution, and its brain contains specialized neural circuits for processing interaural time differences, the minute differences in sound arrival time at the two ears. Insects, the most diverse group of animals, have evolved a remarkable array of hearing organs, located on various body parts. Crickets and katydids have tympanal organs on their legs, thin membranes that vibrate in response to sound waves. Moths have tympanal organs on their thorax, tuned to the ultrasonic calls of bats, allowing them to take evasive action. Mosquitoes, attracted to the whine of their mammalian hosts, have specialized antennae that vibrate in response to sound, guiding them towards their next blood meal. The evolution of hearing is not simply a story of adaptation to different frequency ranges. Environmental factors like vegetation density, background noise levels, and the presence of echoes also play a crucial role. In dense forests, where sound is readily absorbed and scattered, animals often rely on low-frequency calls that can travel further with less attenuation. In open environments like grasslands, high-frequency calls are more effective, as they are less susceptible to distortion by wind and atmospheric turbulence. Echoes, a common feature of many environments, can be both a boon and a bane for auditory systems. Bats use echoes to navigate and hunt, their auditory systems finely tuned to the subtle differences between emitted calls and returning echoes. For other animals, echoes can be a source of confusion, masking important auditory cues. Some animals have evolved specialized neural mechanisms to filter out echoes, allowing them to focus on the primary sound source. The evolution of hearing is a testament to the power of natural selection, shaping the ear to meet the specific acoustic demands of different environments. It's a story of remarkable adaptations, of intricate structures and sophisticated neural circuits that have evolved to capture and decipher the whispers of the world, transforming them into the rich symphony of sounds that shapes our perception of the world around us. Chapter 5. Echoes of Our Ancestors, the Primate Ear and the Rise of Language and Music. The dense canopy of a Miocene forest, 20 million years ago, vibrated with a chorus of calls. A small primate, our distant ancestor, clung to a branch, its large, forward-facing eyes scanning the foliage. But it was its ears, not its eyes, that truly painted the world around it. High-pitched calls, warnings of predators or declarations of territory, echoed through the trees, each carrying vital information. This reliance on hearing shaped the primate ear, setting the stage for the extraordinary auditory journey that would culminate in human language and music. These early primates possessed a short cochlea. This short cochlea was ideally suited for detecting the high-frequency sounds that dominated their arboreal world. The calls of insects, the rustling of leaves, the alarm calls of fellow primates, all were captured and analyzed by this finely tuned instrument. Over time, as primates diversified and some lineages transitioned to a more terrestrial lifestyle, the demands on their hearing began to shift. The open grasslands and savannas presented a different acoustic environment, where lower frequencies traveled further and carried important information about distant events. This shift in habitat drove a remarkable transformation in the primate ear. The cochlea gradually elongated and the overall cochlear volume relative to body mass increased. This elongation, reaching its peak by the early Miocene, enhanced sensitivity to lower frequencies, crucial for detecting the rumbles of distant predators or the infrasonic calls of other animals. The increasing cochlear volume further improved auditory acuity, allowing for finer frequency discrimination and the detection of fainter sounds. The transition to a terrestrial lifestyle also influenced the evolution of the outer ear. The pinna, the external flap of the ear, became more mobile and complex, allowing for better sound localization. As our ancestors ventured into more open environments, the ability to pinpoint the source of a sound became increasingly important for predator avoidance and for locating potential mates or food sources. The pinna, with its intricate folds and ridges, acts as a directional antenna, modifying the incoming sound waves and providing cues about the sound's location. The most dramatic transformation in primate hearing, however, occurred with the emergence of language in the human lineage. Our ears became exquisitely tuned to the frequencies of human speech, a range typically between 1 and 6 kHz. This sensitivity allows us to perceive the subtle nuances of spoken language, the variations in pitch, tone, and rhythm that convey meaning and emotion. While other primates also communicate vocally, their vocalizations are generally less complex and cover a different frequency range. The specialized auditory processing in humans, reflected in the unique organization of our auditory cortex, allows us to decode the rapid stream of sounds that make up spoken language, a feat unmatched by any other species. Intriguingly, humans exhibit an unusual trend in frequency selectivity, the ability to distinguish between closely spaced frequencies. This selectivity is particularly pronounced in the frequency range crucial for speech perception, suggesting that the development of language may have played a role in shaping this aspect of our hearing. This finely tuned selectivity allows us to differentiate between the subtle variations in vowel sounds, for example, a crucial element of language comprehension. Research suggests that these human-specific patterns of frequency selectivity may have been directly influenced by the evolutionary pressures associated with the emergence and refinement of spoken language. Music, another hallmark of human culture, has also left its mark on our auditory system. Our ability to appreciate melody, rhythm, and harmony is a testament to the sophisticated processing power of our auditory pathways. The tonotopic organization of the cochlea, the precise mapping of frequencies along the basilar membrane, allows us to perceive the different pitches that make up a melody. The timing precision of the auditory nerve fibers, which transmit signals from the hair cells to the brain, enables us to detect the rhythmic patterns of music. The intricate connections between the auditory cortex and other brain regions, including those involved in emotion and memory, contribute to the profound emotional impact that music can have on us. Interestingly, humans, along with apes, are unusual among mammals in our relatively limited ability to hear very high frequencies. This loss of high-frequency sensitivity is likely a trade-off in our evolutionary history. As our ancestors prioritized the lower frequencies crucial for speech and social communication, the selective pressure to maintain high-frequency hearing diminished. Humans, with our larger heads, have a greater distance between our ears, allowing us to use lower frequencies for sound localization. This explains why our upper frequency limit is lower than expected for our head size. While we may not be able to hear the ultrasonic calls of bats or the high-pitched squeaks of mice, our ears are finely tuned to the sounds of human voices, the music of our cultures, and the symphony of sounds that defines our human experience. The human ear, then, is a testament to the power of evolution. From the simple gill openings of ancient fish to the intricate architecture of the mammalian ear, our auditory system has undergone a remarkable transformation, shaped by the changing demands of our environment and the emergence of uniquely human traits. It's a story etched in the very structure of our ears, a story that continues to resonate in the sounds we hear and the music we create. Chapter 6: The Future of Sound. The human ear, a marvel of evolutionary engineering, stands as a testament to the relentless power of natural selection. But the story of hearing is far from over. Evolution is an ongoing process, a dynamic interplay between organisms and their environment, and our auditory experiences continue to be shaped by both natural forces and the ever-advancing tide of technology. Convergent evolution, the independent development of similar traits in different lineages facing similar environmental pressures, is a recurring theme in the evolution of hearing, echoing the resourcefulness of nature in finding optimal solutions to common problems. This phenomenon is beautifully illustrated by the multiple, independent origins of the middle ear in different vertebrate groups. Consider the remarkable parallel evolution of high-frequency hearing in bats and toothed whales. Both groups have evolved the ability to hear and utilize ultrasonic frequencies, sounds far above the range of human hearing. However, they use these high-frequency sounds for different purposes. Bats employ echolocation, emitting ultrasonic calls and using the returning echoes to navigate and hunt in darkness. Toothed whales, like dolphins, also use echolocation, but their clicks and whistles serve both for navigation and communication in the murky depths of the ocean. As discussed in previous chapters, the relationship between head size and frequency detection is crucial for sound localization. The hearing organs of insects and mammals, despite their vast evolutionary distance, also reveal striking parallels, showcasing convergent evolution at the cellular level. The mammalian organ of Corti, located within the coiled cochlea, and the insect auditory chordotonal organs, found in various body locations, both utilize sensory hair cells to transduce sound vibrations into electrical signals. These hair cells, despite their different origins and structural details, share a common mechanism of mechanotransduction, the conversion of mechanical stimuli into electrical signals. A fascinating example of convergent evolution at the molecular level is the presence of prestin-like proteins in both mammals and insects. Prestin, a motor protein found in the outer hair cells of the mammalian cochlea, plays a crucial role in amplifying sound vibrations and sharpening frequency tuning. While insects lack outer hair cells, Preston-like proteins have been identified in their auditory organs, suggesting a possible role in sound amplification or other auditory functions. The independent evolution of these similar proteins in such distantly related groups highlights the power of natural selection in shaping hearing to fit specific ecological niches. The differences in hearing organ structure between mammals, lizards, and birds further illustrate this adaptive divergence. Lizards, with their basilar papilla, have a simpler auditory system compared to the complex organ of Corti in mammals. This structural difference is reflected in their hearing range, with lizards generally having a lower upper frequency limit than mammals. Birds, while possessing a more elaborate basilar papilla than lizards, still lack the outer hair cells and Preston-mediated amplification found in mammals, limiting their high-frequency hearing capabilities. Technology, a force of human ingenuity, is rapidly reshaping our sonic landscape, creating new auditory experiences and influencing our hearing in profound ways. Headphones, now ubiquitous in modern society, create a personalized soundscape, isolating us from the natural world and immersing us in a curated auditory environment. This constant exposure to amplified sound, often at high volumes, can have detrimental effects on our hearing, increasing the risk of noise-induced hearing loss. However, headphones also offer benefits, allowing us to enjoy music, podcasts, and audiobooks in a private and immersive way, enhancing our connection to sound in a controlled setting. Cochlear implants, a marvel of biomedical engineering, offer a lifeline to individuals with profound hearing loss. These devices bypass the damaged hair cells of the inner ear and directly stimulate the auditory nerve, providing a sense of sound. The implant consists of an external microphone and processor that converts sound waves into electrical signals, which are then transmitted to an internal receiver implanted beneath the skin. This receiver sends signals to an electrode array inserted into the cochlea, stimulating the auditory nerve fibers at different locations along the tonotopic map, mimicking the frequency analysis performed by a healthy cochlea. While cochlear implants cannot fully restore natural hearing, they can provide access to the world of sound, enabling individuals to understand speech and participate in auditory communication. Virtual reality, an emerging technology that creates immersive sensory experiences, has the potential to revolutionize our auditory world. By combining realistic visual environments with spatialized audio, virtual reality can create a sense of presence, transporting us to other worlds and allowing us to interact with virtual objects and characters in a seemingly real way. This technology can be used to create entirely new auditory experiences, from interactive musical performances to simulated natural environments. However, the long-term effects of prolonged exposure to virtual reality environments on our auditory system are still unknown and warrant careful investigation. Looking ahead, the future of hearing holds both exciting possibilities and potential challenges. Current research into hair cell regeneration and gene therapy offers hope for restoring hearing in individuals with sensorineural hearing loss, the most common type of hearing impairment. Regenerating lost hair cells or correcting genetic defects that cause hearing loss could revolutionize the treatment of deafness, offering a biological solution to a pervasive medical problem. Noise pollution, an increasing concern in our modern world, poses a significant threat to human hearing. Chronic exposure to loud noises, from traffic and construction to amplified music and industrial machinery, can damage the delicate hair cells of the inner ear, leading to irreversible hearing loss. This escalating noise pollution could potentially exert a selective pressure on human hearing, favoring individuals with greater resistance to noise-induced damage. However, such evolutionary changes, if they occur, would likely take many generations to manifest. Technology itself could become a selective pressure, driving further evolutionary changes in human hearing. The widespread use of auditory technologies, from headphones and hearing aids to cochlear implants, is altering our sonic environment and the way we interact with sound. These technologies could potentially influence the development of our auditory system, particularly in early childhood, shaping our hearing sensitivity and frequency range over time. For instance, the increasing reliance on amplified sound could lead to a decrease in our natural auditory sensitivity, as our ears adapt to a louder sonic environment. The future of human hearing is a story yet to be written, a complex interplay between natural selection, technological innovation, and cultural influences. As we continue to explore the world of sound, both natural and artificial, we can expect further evolutionary changes and adaptations, shaping the future of hearing in ways we can only begin to imagine. The research into cochlear size, frequency selectivity, and the evolution of Preston provides a framework for understanding these potential trajectories, offering a glimpse into the possible future of our auditory world. The human ear, a product of millions of years of evolution, is now at a crossroads, its future intertwined with the technologies we create and the choices we make about our sonic environment. From the first whispers of the underwater world to the complexities of human language and music, the evolution of hearing is a testament to life's adaptability. We've seen how environmental pressures, from the density of water to the rise of technology, have shaped the ear's intricate structures and functions across species. This journey illuminates not only the biological marvel of hearing but also the interconnectedness of life on Earth. Where will our sonic journey take us next? Share your thoughts and questions below. Like, subscribe, and suggest future topics. Keep exploring, keep questioning, and keep listening to the world around you.